Welcome to our ICAT Playdate. Good morning, I'm Phyllis Newbill. I'm an Associate Director in one of several centers within ICAT. This morning, a couple of housekeeping things before we get started. We are streaming as always. So this presentation will exist online afterwards. It will exist online now. Good morning if you're watching online. And it will exist afterwards, so behave accordingly. There are, of course, pastries and coffee and some tea. Please enjoy those. The way that we can have pastries and coffee and tea is that we have a sign-in sheet, so I'm going to pass that around. Please do sign in on that to let us know that you're here. If you are a Virginia Tech faculty member for whom Professional Development Network or PDN credit is helpful to you, make sure that you, one, sign up for this event. That's online in a separate thing. There's a QR code on the clipboard. And two, make eye contact with me so that I can mark you present. When you have questions, just wait for me to get to you with the microphone so that our friends online can hear us. And if you're online and have questions, make sure you use that questions link. Couple of announcements. There are some flyers around. Oh, also, Winnie is here this morning. There is a little dog. She belongs here. She lives here. It's all good. Okay, seed grants. Roger and Debbie West. Student seed grants are due February 13th at midnight Eastern. That is a hard deadline for student-led transdisciplinary projects. If you have questions about that, you can see anybody at that back ICAT table, talk to me, or go to the ICAT website. Also, there's a flyer around on some of the tables called about AI ethics and policy through Applied Theater, some workshops that are coming up February 13th, 20th, 27th, and March 6th at Theater 101. So if that's something you'd like to explore, I think you will get an Amazon gift card for each session that you attend, and we're hoping that you'll go to all 4 of them. So if you have questions about that, there's some flyers around. At this point, I'm going to turn it over to one of our most senior, most senior. He's been here forever. I think my first meeting with any ICAT thing was with Chris Williams. So I'm glad Chris Williams is here with us to talk about how 3D printing has changed so much over the last zillions of years.
Zillions, man. Thanks so much, Phyllis. I feel
You're welcome. You're welcome, Chris.
So young and innovative. All right, we're going to start off with a question. What is keeping you personally from 3D printing everything? What's keeping you from 3D printing stuff? Because things fall down? Is that your gravity is the answer? Yeah, like can't print stuff in the air. Okay. What other limitation do you face on a daily basis? Okay. All right. What else you got? What other reasons are making you? Why aren't you making everything with 3D printing? What keeps you from doing it? It's too expensive. It's a lot of plastic. Thank you so much for that one. I'll pay you later.
I don't own one, and I have not done any of the training to access any of the studios, and I don't have any time.
Thank you, Tim. All right, so we'll pay you both afterwards. Yeah, so one challenge might be doesn't have the materials you want. Another reason might be it's too expensive. Another reason is it does still require a lot of expertise, although that's getting a lot better in the plastics world. But did you know you can 3D print metal? And so that's an image on the left of something that we made at Virginia Tech. You can make really large things with metal printing, and this is not extruding molten metal out of a nozzle. It's actually, in this case, literally a welder duct taped to a robot, and just like plastic extrusion, it's depositing metal layer by layer, and people are using it to make things like bridges and propellers for Navy submarines. So the way this works is, this is actually one of BIMNet's prints, printing layer by layer just like you normally would, but it's actually a wire arc welding. On the next click, you'll actually see a slow-mo video. We're literally dipping wire and having a big electric arc that creates a plasma that then locally melts that metal, and I can literally just, almost like needlepoint, I'm depositing metal bit by bit by bit, really quickly, layer by layer, to build up metal parts. And the challenge with that process is it is expensive, although it's not as expensive as other metal processes, because it's just a welder duct taped to a robot, perhaps, but it does require a lot of significant expertise to operate that machine, use it, and even when you're done printing, if you have all that expertise in the tool pathing, the metallurgy, and all that stuff, you actually have to then have another expensive machine like a vertical bandsaw to cut that metal part directly off the plate. It's actually welded to the plate. So it requires another piece of equipment just to get the part off. And then after that, you'll have to do some additional machining to sort of clean up the surface. You can sort of see it's rough to get to the final shape you want. So the question we asked is, what if you could really lower the barrier to metal 3D printing the way that we did for plastic 3D printing almost 10 years ago? So that's the question we'd like to propose to you today and what our team worked on. And this team was led by Bimnet Mola, a PhD student in our group, alongside Ian Ho, another PhD student in mechanical engineering, and our collaborators, Lisa McNair in engineering education, and ICAT and Cine, and Brooke Kennedy in industrial design. So on the next slide, what you'll see is 2 key innovations helped us get to that point of lowering the barrier, and they both belong to this very smart PhD student, Bimnet, here. The first one is that Bimnet found a way to set the settings of the welder such that it doesn't weld directly to the part very strongly. So in the video, he found a way. Traditionally, you cannot remove the part off the build plate. You have to go to that bandsaw. But what Bimnet discovered was a way to actually have a very loose weld on that first layer that allows you to literally just remove the part, maybe not always with your hand, maybe a tap of a hammer, but allows us to now completely skip that second machine and that expensive cost and that expertise and that danger. You can literally just tap the part off the build. The second innovation that Bimnet worked on, along with some other students in the group, was design. That 3D software has another barrier to entry. Forget operating the machine, just learning how to design things. So we said, you know, if you could just have a napkin sketch, a 2D drawing, and you could take an image of that, could we create software that automatically takes in that sketch, populates as many layers as you want, and then automatically generates all the instructions to the machine to actually print it in metal? And so that's the big idea of sketch to print in metals. So what we did is actually created a graphical user interface that allows you to do that automatically. So you literally just upload your camera photo and work through all the process to actually finally get to step 4, where all those instructions get sent to the machine. And in this case, we actually had a high school student intern work with us in the summer to actually get that done, which is super cool. And I'm going to pass it to Bimnet on the next idea we had, the third innovation, if you will.
So one of the things we did, as Dr. Williams just spoke about, is create this workflow for sketch to metal 3D part. But in the world of design, if you're working on a computer, we don't really, or at least I can't visualize what a millimeter actually will look like from the computer screen to the physical world. So one of the things we did to progress that is incorporate a projector into our design space or into our print space so that we can actually project the design that we want to print and manufacture. This allows us to actually work in the real world, kind of like augmented reality. This is a very V1 step of that. And we can project that drawing, and the machine is 1-to-1 scale with that projection, so we can actually print the physical, wherever your hand goes is where the machine will go to print that design. And that's what it looks like in real life. So we've tested it. We've manufactured some parts of what you're actually looking at. Actually, I will say that, but this is the printing process after we've validated the projection, and then once it's done printing, you can walk up to the machine and take off the part as so. So it's a very simple, really easy to use workflow where we're taking the expertise out of the process so that people, as long as you have a pen and paper, you can make this process work for you. To actually design something like this and tool path it, in our lab traditionally it will take several weeks to prepare the file just to be able to print. But we're removing all those steps for early designers, and what you're actually looking at is a design developed by some 5th graders. So what we've actually done is, because we've made the design process so simple, we can actually put this in the hands of users. Part of the ICAT grant, in collaboration with Lisa McNair, is some outreach programs where we brought in a bunch of elementary and middle school students to work with the software. And here you can see them designing their parts. And then in the next slide, we took them to the actual lab so that they could see their parts being printed. So they've seen the entire manufacturing life cycle where they go from design to manufacturing, and they can take some of their designs home. We're not printing everyone's designs, but some kids got their designs printed out.
So working with Lisa and Phyllis, we did a lot of outreach with Cine at ICAT, like Hokie for a Day and then Science Festival. And one of our favorite activities the students came up with was an activity we brought lots of different 3D printed parts and asked the students, hey, is this 3D printed? What's amazing to me over the many, many, many years, I think I heard, infinite years of doing this, is we've changed from no one knowing at all what 3D printing is to now everyone thinks they know what 3D printing is. And so what's great about this exercise is that they all push the metal to the not printed side. But occasionally they'll see something and say, hey, that has layers. So they start to think about this, and it's a really fun way to engage with lots of students across the region in this area. BIMNet also, again, terrific BIMNet, I like to embarrass him a lot, led a lot of summer camps with the SEED group at Virginia Tech and the College of Engineering, which is the Center for Engineering Excellence and Discovery, where we actually got to do a lot of workshops with people who are historically underrepresented in STEM groups in middle school and high school, pre-college students who are coming to Virginia Tech to sort of learn what it means to be an engineering student, and they're actually in the lab, doing the same design exercise. And what's interesting about that exercise is that we have to teach them that, yes, this process is great. It does have some catches and caveats, so we actually teach them about design for manufacturing and engage them in drawing, sketching, and then printing their parts. And then I'm going to go back to BIMNet because he also worked with Lisa on the ID Pro class, which is a pretty cool exercise with Lisa as well.
Yeah, so last year, fall 24 and spring 25, we worked with a group of undergrad students to actually take this past simple designs like you saw in the last slide where they're just simple contours, and we wanted to see what we can actually do in terms of function with this process. So with a team of undergrads across a variety of disciplines from engineering to architecture, we started to think about the fact that we're printing aluminum or metal that is conductive. Can we use the part itself to both structurally enforce the structure and use it as a conductive pathway for electricity? So we did some initial tests where we embedded the metal within the plastic. We were able to build, I can't say this, tensegrity table. So it's essentially floating. It's not contacting each other. The strings provide the tension for it to stand up. And the metal is providing that structure and the electrical pathway. The wires you see here is just for the final contact points between the battery and the structure, and then from the structure to the element that we're powering. In this case, we threw a turbine on there. I would have preferred a lamp, but I was working with a ton of engineering students, and they wanted to put a fan on there. But the main contribution here is we're pushing this past what we thought we could do with this process. Aluminum is very pliable, so you can bend it into the shape you want and use it, again, as a structural reinforcement and as the pathway for electricity. So some really cool things you can do with that process. And the semesters were kind of split up. We had some machine troubles, but the first semester, everything you saw in the last slide, the undergrads did all of that work. It was led by them. And then in the spring semester, we had some issues.
Yeah, so basically Lisa and the team at Cine then proceeded to sort of think about bringing in teachers and actually getting them engaged in 3D printing and finding ways that they could teach some fundamental concepts using manufacturing to support the sort of basics of physics. And that's something actually that's really impactful because now you're not just teaching one student at a time, you're teaching the teacher who then can go back to their classroom and continue to disseminate that. So some great work from Lisa and the team. And what's also nice about that work at ID Pro is that interdisciplinary then brings additional new ideas. You know, here we are thinking about doing contours, but now coming up with additional multifunctional ways in which to engage this process into systems or architecture is pretty exciting. We've also taken this to classrooms at Virginia Tech. So this is an added to manufacturing senior level course. And the challenging thing in all education is how do we get experience? If we sit there and just teach them on slides, how do we actually get their hands dirty, if you will? So in this case, we're actually teaching them about structural optimization, which normally requires a lot of learning of software, and we never really get to the point of actually testing their designs. But BIMNet came up with a great idea where we gave them a load case and some obstacles, and they had to actually literally just by hand sketch what they thought would be a most structurally efficient solution, which we could then immediately take to the printer, print that out in, I don't know, 10 minutes, and then put it under the arbor press and actually get them to test and get a feel for what that does. But BIMNet and the team have actually supported lots of folks across the university and some engineering ideas like this big spring, sort of helical spring idea, and you worked on that with Brooke Kennedy and his team, printed jewelry, the printed sign, and as BIMNet mentioned, the idea that you could actually print this objects flat and then actually, because it's so pliable, sort of bend them into shape, and then you use traditional welding to sort of join them together to make, in this case, a nice wall hanging for one of the other students for fun. Another collaboration that this enabled, because really what we're doing in our lab is we're creating these new capabilities in what we think are design tools, but we really need to work with designers to think about how to implement them. So I'm really excited to see some architecture students here in the front row, because we'd love to have your ideas on how to actually put this to use. One way in which we've worked with architectures with Yasamin and Nathan King in the CDR at architecture, where we were actually working on a printed podium. We wanted to have a 3D printed like lectern for a big conference we were putting on in September. And so over at the CDR, there's this big 10-foot robot with a 100-pound per hour deposition tool that can actually, print plastic. So imagine you're 3D printing plastic, but now at a much, much larger scale. And Yasmin and our student Nima actually came up with this really beautiful, elegant design, and it was really cool and printed really well. But then we noticed one interesting challenge was, podiums are not supposed to do that. So what do we do with that? So actually, again, working with that new technology of large-scale polymer printing, they then came over to BIMNet and said, hey, is there a way that we could reinforce this afterwards? So BIMNet and the team literally just sketched by hand ideas about how to reinforce this, printed it, and then actually heated the metal up and then heat set it into the plastic. So now actually we have a fully structurally sound, elegantly, beautifully reinforced structure. So now we have two material systems all printed that enable quick discovery and quick solutions to interesting problems. And in theory, we could have run electricity to this as well. So really what this project is all about is trying to democratize metal printing. How do we get this in the hands of as many people as we can through not only reducing the amount of knowledge required to run the machine, but also the design, going from design to print, also completely eliminating the need to actually have to do a dangerous bandsaw cut, just literally knock it off the part. And along the way, we got to do some really great work with getting people to learn about advanced 3D printing, changing their ideas about what it can and can't do, talk to them about the new world of metal 3D printing, maybe getting them excited about a career of taking their sort of 3D printing hobby and then seeing how it could translate to an engineering profession or an architecture profession, and that's been really exciting. So before we go to this last slide, I just want to have one final note. As was mentioned by Phyllis, it's funny, actually, I was teasing you, but really, this is the very first grant I ever had at Virginia Tech.
Video start.
And it was funded by the precursor to ICAT. And we should mention, Phyllis, if you know about that, that means you've also been here a long time. And this was the first ever desktop scale 3D printer. It's made, it's called the Fab at Home. And it's literally a syringe on a laser cut acrylic frame. And it was made by a friend of mine at Cornell at the time. And so this small seed grant that we got from the precursor to ICAT allowed us to buy this kit, build it, and then we took it to a bunch of outreach events. And at this time, we were actually printing Cheese Whiz onto crackers on demand. And it was at the time to educate people what 3D printing was, what the idea of layered manufacturing was. And now, not so long, we've come to this world of being able to still engage students, but now teach them about the next evolution of 3D printing and creating tools to engage them in learning, but also engage them as designers and creators, thanks to great students like BIMNet and great collaborators like Lisa and Brooke and Nathan as well. And with that, we'll pause and take questions. Thanks so much.
Am I seeing correctly that mostly you're printing aluminum? And then I have a second question, was it just about the aesthetics of it? It looks like it's pretty ropey. Is there a way to, or is there a process that's happening now to kind of make a smoother surface? Or can you talk about that?
Yeah, so all the parts that you're seeing today are of aluminum, but this process is generalizable. So we have started working with steel. We can do this with any material that exists in terms of, for metal. If it exists in welding wire, we can process it using the same processing technique. So we have some ideas where we want to use the steel as a rebar structure. So if anyone's in construction or civil, one of the ideas is, can we embed the steel within the cement the same way we're embedding the aluminum within the plastic? So some really cool things there. In terms of the texture, this kind of goes back to the original slide. Yeah, right here. We're actually, the way we're approaching this is we want to use the texture as a design feature. If you wanted to have more smoother surfaces, you have to go back to the more traditional way of using this process, build a chunkier piece of metal, and then go back and machine it. So it's one of the limitations or constraints of the process. If you want a smooth surface, we got to go back to the more traditional way of processing. Good.
You guys said that you changed the first layer so that you don't have to cut it off anymore and you can just take it off. Does that create any structural issues? Does it ever tip over because it's no longer like adhered to the build plate?
Yeah, that's a really good question. So part of the reason traditional manufacturing permanently welds it to the build plate is due to residual stresses that will actually have it delaminate off the build plate. So the first layer is at risk, and in some cases it does start to delaminate, but it won't fully tip over because it's a big enough structure on the first layer. What we're doing in subsequent layers, 2 through whatever, we're actually using another set of unique processing to reduce that residual stress to prevent it from delaminating. So there's a lot of, my entire PhD is trying to solve that problem, essentially, so.
Yeah, on that note, there's a different presentation that's his defense, which is all the physics and all. It's not just magic. It's a lot of really excellent science and engineering by BIMNet and modeling so that it can be adaptable to no matter what the material is. You can get this kind of really unique behavior that really no one else has ever seen. And BIMNet's first idea to use this was, hey, we could actually use it to just quickly print art. And that's what this is all about at ICAT is, doing some really great, maybe in this case, engineering and science, and then translating it to work with really, creative folks to actually think about how we can use it as a creative tool. And the other presentation is a bunch of numbers and math and physics, and at the end we say, oh, by the way, you can also make this really cool stuff. So this is the inverse of that presentation.
I'll be there in a minute.
With what you're doing right now, how much money and time are you saving or potentially saving with doing this compared to like just regularly using a welder?
I don't know if there's a real answer to that. We're not competing with the traditional way of manufacturing. So we have, on the other side of my PhD, there's some other work that we're doing where we're using the same processing technique to build more chunkier parts, kind of answering the original question from her right there. But in terms of some other work we're not going to speak about today, we're saving a lot of time and money. Within the process that you've seen today, we're not competing with traditional manufacturing. We're really presenting a new novel idea. So there is no metric on time saving and cost saving.
And the challenge with cost questions is always comes down to how do you define the boundaries of comparison. So if you're just looking at the printing side versus, but if I took into consideration obviously we're eliminating that post-process step, so that's like a couple, $50,000 machine, but also though we're limiting the need for the training required to do that. And on the front end, same thing, we're actually skipping all the need. You can just come in with a piece of paper and get to printing immediately. So there's also the costs associated with that are now completely gone. But more importantly than that, the cost, I think, is just opening the door to more people to use it who couldn't have access before, which is what you all don't remember this. But in the early days, like in 1997, was my first experience with a 3D printer, and it required a full-time technician. That same exact technology in that printer, fast forward just a few years, is something that my young child can run with an app on his phone. So it's pretty exciting stuff.
From the 1900s, really?
The 19-aughts, yeah, no. Come on.
You two need a podcast, and you go at each other. So as this process gets more refined and smaller, where do you see the convergence with etched printed circuit boards and things like heat sinks and electronics?
And you mean like a joint radio show on FM radios? Okay, here we go. Back to that question.
So at the size scale that we're printing at, we will never reach small enough for printed circuit boards. We're thinking more on the large scale power electronics because if you've held the parts in your hands, the layers are they can go from 2 millimeters all the way to 10 millimeters in diameter. So we're looking at more like gauge wire applications and using that again for the conduction and then the structural reinforcement. So we're going the opposite direction. We don't want to go smaller and smaller. We want to go bigger and bigger. And that's just a limitation of the process. There's a point at which 2 millimeters is probably the smallest we can consistently go. Sweet. And actually, to add on to your question, so in terms of the cost, there's actually, if you look at the parts, what we're really doing is just bending the metal. There are traditional processes that we can compete with in terms of just wire bending, but those machines are also 50, 100, 150K. So we are reducing the cost in terms of the democratization, opening the technology field or the technology space to people who traditionally wouldn't have access to some of that equipment. So again, there's no real metric, but I guess we can compare with some traditional manufacturing where we take some aluminum sheets and then bend them into the form. But that goes back to the technical expertise. You need a lot of people who know a lot of really good science to be able to manufacture some of these things.
Very cool stuff. So the tool that you made, the web interface or app or whatever it is, to do this, yes, is basically just taking a 2D drawing and extruding it, right? Are you thinking about taking this into the third dimension rather than just pulling it into that, or to be able to take drawings or maybe multiple drawings and automatically create toolpathing from just 3D sketches?
Yes, there's a part floating around somewhere that has it twisting in 3D space. Yes, yeah. So yeah, what you're seeing on the screen is just doing a simple extrusion, but we do have add-ons where we can start to alter a single sketch and rotate that. And then future iterations, we're hoping to be able to incorporate sketch 1, sketch 2, sketch 3, and bring it all together.
Coming your way.
Oh, okay. Hi. Chris, it's good to see you again. And, you know, I'm so long around Virginia Tech. The first time I saw 3D printing, it was chocolate that was being printed over. And I thought, well, this is the dumbest idea I've ever seen. This is never going to amount to anything. So don't ask me about investing in companies or technology. What I'm interested in about this technology is how close is it to being accessible and for purchase to be used in a makerspace or something like that, where it really is democratized and people could have a membership or use it at the Virginia Tech makerspace in the library.
Yeah, so I think the cheapest work cell right now that's available is maybe $30,000, I think. Maybe it's probably more than that. It's probably this cost of the welder. Okay, I was trying to be $60,000. And it does require ventilation as well, and like you can't look into the arcs. You have to have ways to protect people from that, but we can do that with fifth graders. I think we can do that. So on that note, we are creating that new building over there, Mitchell Hall, that's being built. It will be open in 2 years. It will have a very large manufacturing studio, which will have one of these systems that will be more available to folks than in our, because right now the only systems that exist like this on Virginia Tech campus are in our lab. So we are in the process of creating spaces to give people more access that could use this software. But yeah, fundamentally, at the end of the day, this is welding. It is dangerous for the eyes. It can be dangerous for the lungs, so you would have to install with this. So it's not going to yet be at that desktop in your garage level. But fundamentally, this idea of 2D sketch to immediate printing is something that I think it was available on some website as well for polymer printing. This is the key part of, in this regard, is actually all the instructions that take that blue line and give it all the detailed instructions about how to create that removable component, and that's something that we can also make available on the web for other people to use who have that system. Yeah.
We are at time, so I do want to continue the conversations with, after we close. So I want to thank everybody for being here this morning. There's still some danishes and pastries and things over here, so please continue with those. Please continue the conversations. Thank you if you're here online. Hope you have a great weekend. Stay safe in the snow, and we'll see you next week, with the same stuff, but new topic. Thank you.